Sonic, the heart of your system.
TECs or thermal electric coolers seem to kind of have a comeback, at least judging by the comments here on my YouTube channel. So recently a lot of people asked me, hey, can you do a video about TECs and what they are capable of? So of course we can do that, and that's why we are here today. So first of all, what is even a TEC? TEC is the thing I'm holding in my hand. Basically consists of two aluminum oxide ceramic plates, which are the white things you can see here, and you can see the cables coming out from the back. And it's a semiconductor, so whenever we apply a voltage to the cables, we will generate a temperature difference between the two plates. It's also sealed on the side by some silicone glue. It's basically because most of those are usually used below room temperature applications. Therefore, it's possible to have condensation on whatever you cool with it, and also condensation on the TEC itself. That's why it's sealed, to prevent it from short circuits. This is one of the biggest TECs I could find out there. It has a power consumption of 360 watt using 12 volt power supply. 360 watt is a lot. That's why we need those very thick cables. So as I said before, by applying a voltage to the cables, we will generate a temperature difference between the two plates. And the colder we keep the hot plate, the colder the cold plate will be. So for example, this one can generate a temperature difference of up to 70 Kelvin. So if we keep the hot plate at 70 degrees Celsius, then the cold side will be 0 degrees Celsius, which is quite a lot. Obviously, the temperature difference also depends on the load which you apply to the cold side. Also, what's very important is that those things are most efficient at 50% load. So using a 360 watt TEC, you should not apply more load to the cold side than 180 watt, which is basically what we typically get on an 8700K with decent overclocking. Now the problem is that we cannot put this thing directly on an 8700K, mainly because the contact surface is a lot bigger than the 8700K, while the thermal conductivity of the aluminum ceramic is not that great. So we need something to spread the heat of the CPU across the whole surface of the TEC, and then also cool the hot plate of the TEC sufficiently. That's the reason why I designed my own water block for this around 4 years ago. I did not really have time to pick up with this topic during this time, but now, because I got so many comments, I got it out of the drawer for you guys, so we can test what it's actually capable of. The design is really simple. So we have a thick copper plate on the bottom, which is used to spread the heat of the CPU across the whole surface of the TEC. And in the bottom plate of the copper, there is also a temperature sensor included. Then we have the cover of the water block, which will have the second copper piece inside here, which has a lot of water channels to dissipate the heat to the water. This is exactly what we have inside the water block, so the big TEC. And you can see I have two 8-pin PCI Express connectors attached to it. As I said before, 30 amps are flowing through this TEC, so we need a lot of cables, very strong cables. Typically you should not utilize the cables with more than 6 to 8 amps per cable. So that's why we need two 8-pins, just to be sure. Applying a constant voltage directly to the TEC is not really an option, because we will instantly reach the region of condensation, which is what we want to avoid. And that's why I designed this controller for the TEC. It's very simple and only consists of 3 parts. So we have the temperature controller itself here, we have a solid state relay on here, and a water block on the bottom, which is cooling the solid state relay. So the 10K temperature probe goes into the controller, gives it an indicator when it has to switch on and off. And this controller is then turning off and on the solid state relay, which is then controlling the TEC itself. The problem is that the solid state relay is not that efficient, so it also has a quite high power consumption of around 30 to 40 watt, which means that we have to actively cool it. That's why there is an additional water block on the bottom. That's what I used for prototyping around 4 years ago. It's not the most elegant solution, but it's a very cheap solution, because a temperature controller like this costs around 30 euro. The solid state relay is around 15 to 20 euro. And then we have another 20 euro for the water block. So it's a fairly cheap solution just for prototyping. Of course, if we want to use this in a system, it's not a great solution, because it just takes up so much space and the solid state relay is not so efficient. So I got in contact with Elmore, who then designed a TEC controller for me. So it's a small PCB with MOSFETs on there. The MOSFETs are actively cooled by a small cooler 40mm fan, and we simply have input and output. So input 12 volt with 3 6-pin connectors, and then we can solder the TEC to the other side, and then we also need the temperature probe as input signal to the TEC controller, and we can freely program the TEC controller to whatever temperature we want. Typically we keep it in the range between 16 and 20 degrees Celsius. So whenever it's heating up, it hits 20 degrees Celsius, it starts to cool down. Whenever it hits the point of 16 degrees Celsius, it switches off, so we do not hit the region of condensation. It moves back up until it hits 20 degrees Celsius again, cools back down, and that's how it continues. So what is such a TEC cooler really capable of? I mounted my TEC cooler on an 8700K. The 8700K is heavily pre-binned, so I know that it was capable of around 5300, 5400 megahertz under water cooling conditions. And mounting the TEC cooler is exactly the same as mounting a normal water cooler, so just used 4 screws to mount the TEC cooler. Then we have to attach the cables to the TEC controller, and of course also mount the temperature sensor on the TEC controller as well. The whole setup is then cooled by 2 360 radiators, which is mainly needed because as I said before, we have 360 watt power consumption of the TEC, and we have a peak power consumption of around 250 watt of the CPU. So total power consumption around 600 watt, which is quite a lot. So we need around 2 360 radiators to have a decent water temperature. So in BIOS I clocked the CPU to a base frequency of 5.4 GHz, and if we go to temperature monitoring, we can straight see that the CPU is 18 degrees Celsius core temperature, which is already really nice. Then I set the load line calibration to level 7 to make it really aggressive, set current capability to 140% just to make sure that the system or the mainboard will not power off with the heavy overclock. I adjusted the CPU core voltage to 1.37 volt and the VDIM was 1.6 volt because the memory was also quite heavily clocked to 3.8 GHz at CL14. In Windows I opened Cinebench, Core Temp and CPU-C. As I said before, CPU clocked to 5.4 GHz. Real voltage applied to the CPU was now 1.47 volt including load line calibration, and you can see in Core Temp temperature is typically something between 13 and 18 degrees Celsius, which is extremely nice. Then performing a Cinebench R15 run, temperature ramps up to about 55 degrees Celsius, which is still really nice considering that this is 5.4 GHz at 1.47 volt. Score in the end 1752 points is really solid considering that this is a 6-core CPU. Then I clocked the CPU to 5.65 GHz because I wanted to perform a Cinebench R15 single core run to see where the single threaded performance is at. And running R15 single threaded test, one core hits around 30 degrees Celsius while the other cores stay really cold, and the final score is 246 points, which is extremely solid. Then I ran again multi-core test at 5.5 GHz, which resulted in a score of 1790, which is almost 1800 points for a 6-core CPU, extremely good. I tried to run 5.6 GHz, which then resulted in a crash in the end, so unfortunately 5.6 GHz is not possible. So some of you might think, hey, why do you not stack several TECs on each other to reach even lower temperatures? The problem is, as I said before, they are most efficient at a load of 50%. So we cannot just stack 2 360 watt TECs on each other. Result would be absolutely terrible. But what we can do is we can use a smaller TEC and put this TEC directly in between the CPU and the CPU cooler. This TEC is only capable of 96 watt, so it's not that strong, it's not that great. It will not help us to perform Cinebench multi-core runs, but we can really cool down the CPU and see what we can just get frequency-wise. So I went back to Windows, applied a voltage of 1.47 and then clocked up the CPU in 100 MHz step, 5.6, 5.7, 5.8 GHz, then 5.9, and in the end I could reach 6 GHz. Unfortunately, 6 GHz was not stable for more than around 5 seconds, resulted in a blue screen, which is probably due to the very low core voltage for this frequency. So 1.47 volt is fairly low for 6 GHz. I think if I would have pushed it more to maybe like 1.5, 1.52 volt, it should be stable for a longer time period, but it just shows what TECs are theoretically capable of. So would I recommend putting a TEC in your daily rig? Absolutely not. As I said before, efficiency is absolutely terrible. 360 watt additional power consumption for 100 to maybe 300 megahertz more CPU power. Not really worth it. It's a fun thing to play around with if you want to reach overclocking records or you just want to see what your CPU is capable of. Really fun to play with, but not for your daily rig. We were actually thinking of making 50 to 100 of those units just for people who love to play around and experiment with those things. So if you're interested in this, please leave a comment down below. Maybe we will do it, just let me know in the comments. So that's it for this video. I hope you enjoyed it. See you soon.